right?
All right, so today we're going to have a tutorial by Catherine Thome on fast ion analysis in OMFIT via the TRANSP, FBM, Birth, Alcon, and ICE modules. Take it away.
Cool, awesome. Well, thank you guys all for coming. So I just wanted to give this tutorial because there's a lot of fast ion modules in OMFIT, and I don't think a lot of people are aware of that. I watched some of you guys recreating the wheel, and so you're the inspiration for this. And so this is not an exclusive list of the fast ion modules. This is the ones that I'm the most familiar with. I know there's FIDA-SIM, but that could probably be its own tutorial by itself, but these are the ones I think that are really helpful to go through. So for today, I'm going to go through a shot in time that I've analyzed looking at ICE data, and so we'll go through all these modules taking a look at that shot. So to start out, just so you guys are familiar with what the shot looks like, this is a limited L mode oval plasma, typical fast ion discharge. We have an IP ramp. BT is 1.3, density is pretty flat, but then we have different beam blips. So in particular, we're going to be looking at a beam blip when 30 right is on at 2.64, so right around here. So now that we're going to start off with looking at TRANSP and the TRANSP related modules, because those are the most important ones I think for people to use on a regular basis. So there is an OMFIT TRANSP tutorial, and you can find it by just googling OMFIT TRANSP. You don't actually have to go to the website. You come here, it brings up the page, and then if you scroll down, you can go to the tutorial, click on the DIII-D tutorial, the Google Doc, and then there's a bunch of things in here to get you familiar with looking. This is a 50-page document, so it's pretty extensive, but what I'm going to talk about is just assuming that you already know how to run trans without any fast ions. What do you do when you want to look at the fast ions? So this is going to be looking at the AC files. So the AC files are a separate file that you have to separately request when you want to look at the fast ions. So now going back to no machine, I'm going to open up unstable. So when I do that, whenever I'm looking at something with trans and I want to output the fast ions, just to not confuse it, I usually run a shot without the fast ions, without the AC file. That way, if there's errors, I can fix those by themselves, fix the profiles by themselves, and then deal with the AC file, the fast ion problem later. They sometimes can take a little bit longer to go, and so you don't want to be waiting and then be like, oh crap, I screwed up that name list, or I screwed up that profile. So I'm going to import the TRANSP module. And the shot that we're going to be looking at is from about 1.5 years ago. So it's 172010. And we'll use the default. And so what I'm going to do is I'm going to load an existing run to get the name list and get the U files from. So come here, then I go to File, and then this automatically goes to my TRANSP area on ours, which is really nice. But then I want to click the particular file that I want to look at. So that's 172010 A01. And then I'm going to click the tr.dat file, and then it's going to be putting these things into the OMFIT project to start off with. So this is a really cool way if you're say you have a really big project where you have the kinetic EFIT time, and that's where you did your transfer initially. You don't always have to go to that project. You can just open it again in a new module with trans and start from there. And if you want to make some small changes, it's way easier to do this than to go to your other project, and it's usually a lot faster. Okay? So everything is now loaded in here, and now we're going to go to the input name list. And so where we want to look in the input name list is we want to go to AC file. And so we want to click this enable AC file output because we want to get the AC file. And then we're going to click on this button for the fast ion distribution function, which will output the fast ion distribution. And then when we scroll down, now here are some output options. And so I already know what I want to do for this shot. This is something you want to think carefully about what we're going to do. I know I want to look at I want to average from 2.60 to 2.68. That's what I want to do when the beam is on solid, and it'll just TRANSP will just a new beam will just average over that time period. So there's a bunch of different averaging methods. Two is you give it the last time point and it'll average before that. So since I want to go to 2.68, I'm going to put that out point at 2.68. And then I'm going to put the averaging time as 0.08. And you can actually put up to 200 time points here, and then you'll get different birth file and different data file for each one. But sometimes if you're impatient, like I am, I'll just a bunch of different transplants with one time point each. You can only do that for a few, but it's a faster way to do this. So since I only care about 2.68, I want to look at the initial time that we had. So initially I was looking at the whole shot, 1.74 to 5.06, which is not what I care about. So I want to start it up. I care at 2.6. I want to give TRANSP enough time for new beam to get started. So I'm going to say 2.3. And I only care to 2.68. So I'm going to set this end time as 2.69. Okay. So I've changed the time just to reflect on what I was doing. And now I'm going to look at the heating. And so when I did this by default, I used the predefined fidelity of medium for the fast ions. And so let's look at the expert user and see what this actually says that we are using. So this means that here's our GUCON, and then here's our number of rays, and the number MPTCLS. But then if I want to change these parameters, like let's say I was doing a quick run, I just want to get an idea, but I want to do something more, I would change them here. So this is end depot and the number of particles. And after I'm done thinking about that, I would go back to the AC files, and then I would make sure that I set NL depot gather and LNL end depot max gather accordingly. So there's a checkbox here, and the reason why I'm bringing this point up is one time I forgot to set this parameter, and I had a shot where there's two beams on, and when I was looking at the birth, there was only one beam on, and I was scratching my head, I couldn't figure it out. Then I spent a bunch of time reading the TRANSP name list page, and then I realized that this is an important parameter. So you should make sure, and there's a formula you're supposed to follow up here. It's in the tutorial as well, but it tells you what you want this to be. And one thing about this parameter is when you set it higher, it takes a little bit longer for it to run, but you want to make sure you actually have all the particles that you care about. One thing, TRANSP doesn't know how many particles you can have, so they claim that if you set this too high, things can break. I've set this into 200,000, but I haven't set it much higher than that, so. This is just an important parameter to pay attention to, I found, especially if you want to make sure you're capturing each beam. So then we've now set up everything that we want to do. So we submit it like we normally would. We prepare it, and then we run TRSend. I'm not going to do that now. I'm going to assume that you guys know how to send TRANSP runs. If not, I'm going to refer you to the tutorial that talks about this. So this was just talking about the TRANSP tutorial. TRANSP by itself is a standalone. Does anyone have any questions about how to make these AC files? Okay, great. So the next thing that we're going to do is, let's say I just sent that run to Princeton, and then it's done. I get an email, it's done. And so AC files are a little bit different than regular TRANSP run IDs. Everything else is in MDS Plus, but AC files are not put in MDS Plus. You actually have to fetch them from Princeton. And so there's two sections in the tutorial about TRANSP. There's the first one about making it, which is just everything I went through. But then there's another section that talks about using the birth and the FBM modules to look at the fast ion. So after the run is done, you actually want to fetch the data, and the command is tr_fetch, then DIII-D, and then run ID. And when you do that, I will show you what you get. You get a folder. These are all the files that you get back. There's a way to be fancier about this and not get all these files, like you don't need all these files, but it's easier just to remember tr_fetch. The two files that we really care about are the birth file right here, and then the .data. So this is the fast ion distribution, and then here's the birth file. So if we had put 2 times, then you see this increment 1, there'd be a 1, there would be a 2, and then data would be either a 1 or a 2. So that is what would happen when you look at it. Okay? Now let's look at the birth and the FBM module. So the birth is the birth profile. So that is, you have these really fast ions that are made from the neutral beams or the RF ions. What are they born? Where do they start out with? And that's what the birth profile, birth module will tell you. And then the FBM is kind of, it's an interesting, I was trying to figure out what this stood for, but the F is actually like the distribution function, like the distribution function of like the fast ions, and then BM is beam, the distribution of the beams kind of is the way to think about that. So now coming back to our project, there is TRANSP, and so actually both FBM and birth are actually daughters of the TRANSP module. So you can just click on them there and open them, or you can import the modules by themselves. These modules are pretty small and pretty fast, so I prefer to load them by themselves, but that's not something that you have to do by default. Okay. Now there's birth, we get the GUI, we just double click to get the GUI, and now we need to pick the birth file. So we want to get pointed to that file that I just showed you in my directory. So we're gonna file, and we have to of course go to a different place. So at least on Iris, there is the XPSI, and then there's an energetic particles area, and then different people have different areas. Then I have TRANSP, and then I have for all of my run IDs, I put them here, that way other people can access them, that way it's not crowding up my home directory and it's not eating into my 10 gigs of space. So we'll click on AO2 to start off with, and this was just what we were looking at before, so I'm just going to click this birth.cdf1. Okay, it's already there, pretty fast. And then there's really only 2 options. The first one is the plot the birth. And so this is going to, again, give you the birth profile and a bunch of the different areas. So first, here is looking at R and Z of where the particles are born, either just generally in the midplane. Remember, this is 30, right? So this is an co-current on-axis beam. I think it was at 75 kilovolts. Not too interesting, but good to know. And then so this one is very helpful to make sure that the beam is where you think it was. So this is when I was saying, when I set that one parameter wrong, I was only seeing 1 beam here when I was supposed to see 2 beams here. So this is always a good sanity check to make sure you're actually getting what you think you're getting of where the beam is. And then the energy is telling you that you see the 3 different energies that we would expect. And then finally, you can see the pitch. So this is just giving you an idea of where the particles are born, and just this is one of the places to check to make sure you set up everything correctly before you start looking at the distribution function. And then there's this other button where you could plot the birth histogram. And so this is something I made, and it bins it here vertically. And so I wanted to see where are my particles being born, where is the median point. And then same thing with energy, is where are the more of the particles born. It's basically here, they're just lines. So here now I know, oh, there's most of them are at this energy. Okay, that's good to know. Now, so we loaded one birth file, and that was fine. But let's say we want to look at a different birth file. So there's this button where you can save the birth to the tree for later use, and you can pick a different birth file. So we're going to go back to this area that I have, and we're going to pick another birth file. This is from AO3. And now we actually have a list editor. So we will have all the ones that we want to put on the left, and then any ones that we actually want to compare on the right. So we can compare AO2 and AO3. AO3 is also just birth, but I'm just going to call it, I'm just going to move AO3 over there. That way it's very clear to me. And then the buttons are the same as they were before. So for my analysis, I was really only focusing on 1 beam. So it's not very interesting because it's pretty similar, but it's good to see that they are very similar. But if you're changing beams, this is a good place to look and see, oh, I changed something. Did it change very much? I think these ones are only spaced out like 500 milliseconds from each other. So this is a pretty simple, lightweight module, but it's a good check of what you're doing and understanding where the particles are found. Now let's move on to the FBM module. So the FBM module is organized very similarly to the birth module. So same thing, we need to know the file. Now let's go look in the tree for where we were. Instead of clicking the birth.cdf1, we're going to click the .data. And then we're going to press this button, extract FBM. So this button is running the get FBM code, which you can also run in IDL, but OMFIT is running it automatically here with these settings. So if you want to change settings, you would actually have to go in the tree, but I think these are the default settings that most people use. So this takes about a minute or so to run. It's pretty fast, but once you run it, you have it for that job. We have it, it's already there. So then we have set the distribution function position as guiding center. It's usually what you want. You can also do the particle position instead, and then you select the R and the Z that you want to look at. So we're just going to use the default and we'll click plot. And what's going to happen is that it's going to give us a bunch of the distribution functions of looking at the beam density. So we have 3 plots here. On the left, we have an RZ space. Where's the neutral beam density? You can see, not surprisingly, there's more density in the core of the plasma than the edge. And you see this red X right here. This is the position that we told it to do. So we can change that number and it will look at different areas. And then on the right, on the top, this is looking at the distribution function as a function of pitch versus energy. You can see like, oh, most of these particles are passing, and that's where they're that's where they are. Okay, good to know. And the scale is density on the left here. All of these have the same. And then down below, this is just showing you a cut line through what is the neutral beam density as a function of rho. So pretty lightweight, pretty simple, but it gives you a lot of information. It's an easy way if you want to compare one distribution function from one shot with another shot. You can look at it here. And you can change these R and Z as you want. And then just like in the birth, there you have the option to save the FBM to tree for later use. So let's pick a different one. Pick A02 again, and we'll do the .data. Again, we can extract it, but so when you make these plots, you can only really plot one at a time. You know, it would be impossible, it would be crazy if you tried to plot more than one. You wouldn't understand what you're looking at. So this is really only to make it handy for you. That way you don't have to keep running the get FBM for each one. You can just have it in the tree, and that way you can go back and forth if you're trying to compare. Anyone have any questions while we wait?
Will there be a way to streamline the Kiara fetch step and not do it manually?
I asked Brian about this, and I think you probably could get a button, but the thing is you want to be careful about where you want to make sure you fetch it somewhere that you're going to have permanent access to.
Oh, sure. You could set a directory in it.
Yeah, that would be something that is missing currently. So
also on the bottom right plot, what do the colors correspond to?
I think they correspond to density, but I
thought the plot was of density versus rho.
I think there's different.
It says it's a function of theta, so maybe they're different thetas.
Yeah, that's what I think. Yeah,
okay.
I think. Yep. I don't usually. The most interesting ones here are this plot.
Yeah.
And so when you have this GUI, again, you can only select one plot. If you have more than one, it'll fail. But then you can just go back and forth and selecting whatever you want to do, whatever position you want to compare the core, you want to compare the edge. It's a nice way to store your data rather than having to keep recreating the wheel. So I'll move on to the next set of modules, but this is the end of the trans modules. Does anyone have any questions about these? Okay, great, fantastic. Okay, so the next module that we're going to talk about is the Alcon module.
I have a question, Catherine.
Yeah, go right ahead.
So when you turn on like heating, like under the NBI tab, like you're enabling the neutral beams, like what does it mean for like beam line equals like 1, 2, 3?
So trans has a different name list for the different beam lines, and so I think it's pointing in the U file to which beam line to use.
Okay, so is there like a standard, or how do we know like which one?
So it should be when you load in a shot. For example, this shot I'm about to show you, I made a kinetic EFIT time, and OMFIT figured this out for me, and I didn't have to set up anything. That is one of the nice things about OMFIT, is it does all that for you, does all that logic for you. The only time you have to use that is, let's say you want to, a lot of people are doing analysis with the new 210s and their off-axis position, and so then they had to know which one to change. But for the most part, those are things that are behind the hood that you don't have to pay attention to.
Oh, okay, because I think it just defaults to beamline 1, right? That
You're talking about in heating?
yeah.
Is it here somewhere? Oh, beamline. Well, I think it's the first one numerically, but I think you can set up the different ones. All the beams are there. It just went to the first one.
Okay, so does it like only choose like a single beam, or?
It chooses the beams that are on in that shot.
Oh, okay.
And that time.
Okay, so you don't need to like really care, like manually choose it.
No, not at all.
All right, thanks.
No problem.
So presumably they used a combo box and a drop down instead of having 14 times 2 A's and Z's in the GUI. So you're just changing the settings of that one beam line at a time. It's also important to know that usually they split up the 8 beams in D3D into 14 beamlets, where the 150s, each source gets split up into 4 beamlets. That's where the 14 comes from.
Okay, thanks.
Any other questions about trans from offsite? In that case, I'm going to move on to the Alcon module. And so for Alcon calculates the alphane continuum. And to run this module, you need profiles and equilibrium file. So that's why I'm starting with a project I already have loaded, because it already has the files in it. I'm going to import a new version of Alcon, but this way those 2 files are already there, and there's a bunch of different modules that you can use to supply the profiles and the equilibrium. So you see the list here. There's a kinetic EFIT. You can also do the G and P files. You can also do it from TRSPL. And then what you can see I have on the left here is these are all kinetic EFIT times. When I have more than one in a project, I like to just underscore the shot number. That way I know what I'm looking at. And so I'm going to select kinetic EFIT time, and I'm going to select 172010, and the time that we've been looking at is 2640. Now I'm going to set up the simulation for what I want it to run. So the default is one process, and this is currently running on one of the worker nodes, so I could actually use more processors. And the continuum model that we have is alphane continuum with the acoustic slowing sound approximation. There's a bunch of different ones here. So Joey, who's sitting next to me, is the person who knows all about this module. So this module was the module, this selection was kind of the one that was the fastest, that had the most amount of physics. So it was the best of both worlds. It didn't take forever to run, but it got a lot of the physics in there. And then radial coordinates roll, the radial range is mostly core of the plasma. There's 200 points here. So this might be something that let's say you want to make your plot prettier, you can change this to get more grid spacing. It would probably be slower than pressure. It can either be from your profiles or from EFIT pressure and gamma I, just a parameter you're setting. And then the toroidal mode number we're setting 4. Of course, good mode number to start with. When you want to look at alpha modes, you can look a little smaller, look bigger. And then we're going to look over a wide range of colloidal mode number space from -20 to 50. And then when we want to look at this, we've currently set the number of off-diagonal terms to 20. And I don't think I've mentioned this before, but you have all these question marks, which when you forget what I'm saying, you can look at these and think about what you want to change them to. But of the parameters here, I think the ones that you most often would probably want to change would be the toroidal mode number, maybe your radial range, and the radial grid point. These are good settings to start off with by default. And these two, 20 and 50, I think Joey did a scan to try and figure out what the best parameters there were to start out with.
I think I just tried to pick parameters that were just kind of overkill in terms of resolution, so that no matter what people are running, typically it's just safe to run with these parameters. So typically you probably only really would change maybe just the top 4 or so parameters up to toroidal mode number, unless you're really interested in the other parameters.
And so now we're going to actually run Alcon. We'll set the plotting options after we run it. So this takes about a minute or 2 to run. One thing I forgot to ask is, what does Alcon stand for? Alphane continuum, kind of?
Yeah.
Okay.
As far as I know, I assume that's what Wenjun set it up for. Or I don't know if there's anything special with the acronym itself.
What is this code doing?
It's calculating the Alphane continuum, which is just kind of similar to just K parallel the Alphane, but it's useful for like if you want to look at like TAE studies. You want to know where your TAE gap is, things like that.
So this code takes a couple minutes to run, but it doesn't take very long, and it depends on how busy or not the cluster is. And you can also change the number of processors to make it go a little bit faster. But you see, it only took 65 seconds, so it only took a minute. And so the result that you get when you start out with is the continuum. It's what's the frequency versus the row of where is there the gaps? You know, like there's a gap right here. What are the different gaps? You know, what frequency are they at? What are they at? So right now this is all gray, which is not what we want. It's a little bit hard to read. So what we're going to go back here to is the plotting options. And instead of the first foil harmonic being labeled at 20, I'm going to set that to 4, and we're going to plot it. And so now we got a lot more color. And so we can look at the different mode numbers that we're seeing, the different colloidal mode numbers, where they are here.
Yeah, so these lines are basically the frequency of the Alphane versus a given radius. And these are just for one toroidal mode number and different M harmonic. And because of basically chronicity, there's kind of a gap between. That's where the gap is where the TAE frequency lies.
There's the different gaps. There's like TAE gap, there's
Yeah.
a BAE gap.
So the bottom gap would be called the BAE gap, and the second gap would be the TAE gap. And above it would be the EAE gap. And I think it's triangularity after that, if you want to go even higher.
These are the main gaps that people care about generally.
So compared to Nova, what is the difference of this coding to physics-wise? What is so fast and Nova less so slow?
Well, Nova does a lot more than this code. This code is really just calculating the continuum, whereas Nova's, I think, also predicting mode structures with the continuum. So that's why it's a lot slower.
This code is good if you just want to get an idea of where the gaps are and, does it match like what you're seeing in the experiment. So you might remember that originally we had an L-mode plasma. So L-mode plasmas don't have a lot of rotation. So we're offsetting the continuum by the rotation. So if we deselect this, it's not going to change very much. But if you have a really highly rotating plasma, you'll see a big change. So here you can maybe see there's a small change between the two. A lot of these modules are pretty simple to run once you get familiar with them, but they can be really helpful when you're doing your analysis. So I'm going to move on to the next module unless anyone has any questions about Alcon.
So one of the steps of running Alcon is running Gatto.
Mm-hmm.
What do you need to run Gatto for?
You have so Alcon requires a booster coordinate equilibrium. And right now, the only way I know how to get that booster coordinate equilibrium is through the Gatto code.
Okay.
I've actually tried to do it myself and failed miserably.
Okay.
So then the final module that I want to talk about is the ICE module. So I'm going to double click on the GUI, and then I'm selecting the shot number, I'm selecting the time range. So I already had one GUI here, so it knows what time range I wanted it to be set to. I'm going to select the channel, and I'm going to downsample the data. So what this code is doing is it's fetching the raw data, and then it's performing the FFT, deleting the raw data, and then it's downsampling the FFT. So on DIII-D, the ICE data is at 200 megahertz. And so if you don't downsample, you have a lot of data. So you can set this to 1 and it works. You just have to be careful when you decide to do that, and is it really necessary whenever you want to do that. And then I'm setting the number of samples per slice, depending on your time range, and you can set these if you care more about frequency or time, you can set that accordingly. But usually the defaults are a good idea to just go ahead and get started. So we're going to press this button, we're going to fetch the data, and then perform that FFT. And so this is using a window function panning. There's noise below 1 megahertz, so I have a frequency filter that automatically only looks at 1 megahertz and higher for this. So this is a pretty short time range, and so it's only going to take about 23 seconds to finish. If we're looking at a longer time, it will take a slower amount of time. So one of the reasons I said earlier I was on the Iris worker node, and that is because when you're on Iris worker node, you have more dedicated resources and it can go faster. One thing I forgot to mention is that for ICE, there is a tutorial on the website. So again, if you just Google OMFIT and ICE, it'll take you to the ICE page, and then you can scroll down, you can find the tutorial, and then this tutorial will go into a lot more detail than I'm going into now. It'll tell you how to check to make sure there's data, because you don't want to go, there's not data for every shot. There's a lot of data for recent shots, especially fast ion shots, but you want to make sure that there's data before you try and fetch a shot where there isn't data, and it walks you through this process, and it gives a lot of examples. We're not going to go into as much depth as was there.
Can you go back to the main documentation page? You go up to the top and click on Run. And go to the public install at GA. And this is just to remind people that there's a section on memory or CPU intensive jobs at the bottom. Yep. And so that's how you get to run the OMFIT on a worker node, should you ever be pestered by the system administrators.
Yes, I have been pestered many times, and my project's killed many times. And so I actually do discuss this in here about how to do it. My recommended setting for what OMFIT, what I would use when I'm looking at ICE data and I want to take over the world. And it works generally pretty well. But the worker nodes are there, and I usually, if you notice, I had another worker node. That was the first OMFIT project I showed you. One was on the medium queue, which is a 1-day queue, and the other one was on the week queue, which is a 7-day queue. The worker nodes are available. They're just sitting there, so I'm just taking advantage of them. Obviously, when there's conference time and more people are doing jobs, I try and be better. If I'm not actually using them, I try not to just have the project open. Okay. So we now have the data, and now let us plot it. So the first thing we want to look at is we want to look at the spectrogram. So I'm going to change the limit of the graph. This is what I generally set it to. There are options. You can subtract the median. You can actually smooth the data. So sometimes if I want to show not like a physicsy plot, but more like, oh, that's really pretty, I'll smooth the plot. So sometimes for conferences, for just like trying to get people's attention, sometimes I'll smooth it a little bit. But here's just looking at the time versus frequency, and then you can see the intensity of the raw ice data. You can see, so ice, it's looking from 0 to 1 to 100 megahertz, and the data in this case is alias, so nothing above, as anti-alias, so nothing above 100 megahertz. So we have the ion cyclotron frequency and its harmonics. So okay, we see we have ice signal. Now what do we want to do with that? We want to actually see how that varies with time and how that varies with frequency. So first, let's time average it. So the middle point here is 2640, and then it's plus or minus 40. And then we're going to plot it. It's going to be a log scale. And so if you remember earlier, the shot was a low BT shot. So this shot actually has two different types of modes. It has what are called compressional or global alpha and eigen modes, which is I think this guy right here, and then it has ice. So you can see that there are some harmonics that we have here. If you look at, there's one that looks like it's at 19, 29, 39. And then if you come back here, you see this is about 9, so they're about 9 to 10 apart from each other. And that we really only see, it looks like maybe to the 4th, you can maybe argue the 5th harmonic there. And there is an option where you can calculate the emission radii. This requires some tuning, so I'm going to plot this. So basically, it's detecting a peak at all these values. And that's obviously ridiculous. That's not what I want it to do. And unfortunately, there's not good settings that work for every shot. You have to hand tune it. So I already looked at the shot in this time to figure out what I wanted, what's the best setting to have to calculate all the peaks. It turned out to be about 5. And so now if I come back to the screen, you'll see that it tells me what the fundamental frequency was, 9.56, and that's telling me where it was emitted from. So it's actually fetching EFITs and it's comparing, oh, here's the B field, where does this frequency correspond to? And so this is handy when I'm trying to see is it core or edge ice. Let me close some of these windows that we have up. So now this was just looking, actually I should keep that one open. This was just looking, averaging over the whole time slice, but now let's look at this frequency. This is about 20. So maybe it's from like 17 to 21. Now I'm going to do a frequency average, and I'm going to set this to 20, and then I'm going to say plus or minus 2, and then we will look at what is the frequency of the second harmonic look like versus time. Often on DIII-D, the fundamental is the lowest, and quite often the second harmonic is the highest. Sometimes the third or even the fourth will be higher. And then you can see here is the amplitude versus time during when this beam was on. So you might have noticed that there was another tab, and this is the beam info tab, and you can plot the power of the different beams to make sure that you know to see what it correlates with. So if you have more than one beam on and you had the signal change, you could look here and be like, oh, what beam was on? So you can see here the power was constant, and then you can see, oh, it's 30 right. And then sometimes we also have variable voltage, and so you can come here and you can see like, oh, what was the variable, what was the voltage at? And you can say, oh, it was held constant. It was at 80 kilovolts that entire time. And there's some more settings that you can click here. You can smooth the data more. On all of these, you can change the scale from being log to linear. I think the log is the easiest way to look at the data, but generally we're looking at ice data and actually looking at the fast ions, but sometimes during the runaway electron experiments, we see Whistler waves, and there the data is usually aliased, and in that case, there's a button, and it'll automatically convert the frequencies so that they are sensible. We don't usually see things that are below 100 megahertz. Usually the Whistlers are around 150, 200 megahertz, and so there's a button that actually does that math for you, because anytime I try and glitch the plot myself, I always get confused. So that was the ice module.
So is the main connection between ice and fast ions that you have these alpha and eigenmodes that the fast ions may excite, or the ice?
So ice is not related to the alpha eigenmodes at all. The theory is still a work in progress, but
But on the ice diagnostics, I thought you said down those lower frequencies.
Oh, so okay. There's two different modes that I was talking about. So I was mostly talking about ice because that's the harmonics, but down here there is something called compressional or global alpha and eigenmodes, and so that's a different instability. Mm-hmm. It's not one that's just frequency. Ice is in pretty much any neutral beam shot on D3D, where the C's and G's are not in every shot. You have to really, they're a problem in spherical tokamaks and SDX, U, MAST. They see them a lot, whereas on D3D, Sean, who's on the line, actually did an experiment to try and study them on D3D. Is on spherical tokamaks that they found that they have a problem where they actually decrease the energy confinement when they are triggered. That's something that we were exploring on D3D. So these are two different instabilities. The theory on ice is not as well developed. There is a theory that maybe there are a different type of instability, that there may be a different visualization of the C's, G's, but we're still working on getting the data and trying to come up with a theory. Because one of the things is this is really fast frequency. Like we're looking at like 50 megahertz here. Like 5 years ago, you couldn't look at this. Computers have gotten so much faster, and then codes are now catching up to actually going to these frequencies to do the analysis too. Probably more than you wanted. Any other questions? Any questions from offsite? Okay. Cool. Short and quick.
Is that what you wanted to show us?
Yeah, that was
Excellent.
everything I wanted to show you guys. So.
Thank you very much, Catherine.
Yeah.